lasers and resonances, or essentially how to track resonances when you have pulsed lasers. So why am I talking about pulsed lasers? A lot of sophisticated instruments nowadays use lasers, and especially as the technology is improving, they use multiple lasers. Here I have shown the case of a Nobel Prize winning technology in microscopy called the stimulated emission depletion microscope. This uses two lasers, a master laser and a slave laser, where the pulse of master laser is followed by slave laser pulse to do the microscopy. Now, how has this improved over generations is that previously if you used only the master laser, you would get these confocal like images where the size of what you're imaging, the smallest size you could image would depend on the medium. However, by employing a second laser, we are able to go beyond this diffraction limit or the smallest size we can achieve, and you can see better features. Now, what is important here is to have one pulse after the other, and for every master pulse, you need a slave laser pulse. This particular relationship of pulse to pulse correspondence or the synchronization and the pulse width become very critical for these systems. To understand how this synchronization is affected and how the pulse to pulse relationship is maintained, I think we should understand a little bit about lasers themselves. In the most simplistic manner to look at lasers, what you can see is if there is optical energy that traverses through the laser, it's going to encounter losses. So you compensate it by introducing gain. Now, in this balanced system, you should never forget that a laser is nothing but a resonant cavity. The repetition rate of the pulses and the characteristics of the pulse itself comes from the fact that it's a resonant cavity. But I'm talking about two lasers. So to get two lasers, you have two different cavities, two different laser cavities. If they don't talk to each other, you'll have two different ring of pulses, one in green and one in red. The only way to bring in correspondence is to inject the information of pulse rates or something through this injection system. So the interaction is brought through injection, and this leads to pulse correspondence. Now, if I look at just the master laser, it's not necessary I operate it at one particular operating condition. What happens if I change the wavelength? Suppose I start by operating around 800. I get a particular pulse rate where the amplitudes are high and it operates at a particular frequency. Now when I move at a lower wavelength, the pulse amplitude drops just because of the physics of the gain gradient. If I move to again 820 and above, the amplitude drops. The frequency for this commercial laser is not in our hands. What will happen if I feed this to the master laser? I feed the pulse trains at different wavelengths to the slave laser and see what happens. Well, what can we expect? Where the amplitudes have fallen, like around the 700 and the 860, you don't expect the slave laser to respond. That's okay. But in the range where the amplitude was reasonable, 740 to 820, you would expect the pulse laser to follow, but that is not happening here. And this is the crux of the problem. What's happening here? Surely the frequency plays a role. Now, you have regions, specific regions of good performance, and how is it that is related to frequency? So in short, the problem we are going to understand is in this two laser system, what is the effect on the slave laser pulse characteristic in terms of pulse width or frequency when you change the master's frequency by changing any of the master's parameters. Right. Let's go back to how the slave laser was. If I said it's a resonant cavity, it should have resonance-like behavior. Resonance-like behavior means if I tune the frequency at a particular resonant frequency, the amplitude should be high and its performance in terms of pulse width should be best. That's what is happening here. In blue is the pulse width, its minimum at this resonant frequency, and the amplitude peaks. So yeah, it's a resonant cavity. Good. But let's look closely. Let's look at pulse width because the amplitude is okay. Let's say that we are going to operate at this particular region where the amplitude change in this dB scale doesn't really matter. Now, the pulse width, however, has a gradual change. It's not a drastic removal of pulses. It's not a single frequency of operation. So what is this that's happening? Let's go back to understanding resonance. Resonance simply is the physical characteristic of the circuit or the system you're seeing. Now, in resonance, what it means is that at a particular frequency, F0, you will have the best performance or best amplitude. If I give an input at some amplitude and some frequency, I'll get surely the same frequency back, it being linear circuit, but the amplitude will change. However, not only will the amplitude change, but if I look at when the next pulse, or in this case, when I talk about sinusoids, what is the difference between the phases or the delay, then there will be a constant delay that will be maintained depending on where you're operating. If you are at resonance, the input and the output will be in phase. When you are not at resonance, they won't be at phase. If you are below resonance, the output may lead. If you are above resonance, it will add. Now, here, this black arrow indicates the output after the resonant circuit. This dotted arrow indicates the input before the resonant circuit. Please keep this in mind because we'll keep revisiting this particular plot again. Okay, what about oscillators? I told it's a resonant cavity, gain is compensated by log. So basically it's a feedback circuit. So you put a feedback, you put a gain to compensate loss. So this is what an independent laser would be. It would just be an oscillator. In oscillators, since the same frequency is fed back and this is whole circuit is at resonance, the phase difference is 0, input follows the output, so this is obvious. What is injection? Injection is where another circuit is influencing this circuit. There is an additional input. It can come from the substrate and so many other sources. It could just be noise. And in our case, we are affecting the master's pulses. In the injection, at the input, with the dotted line, you have the injection signal adding up and giving you the output signal. How does this affect this resonance? Well, first of all, let's ask, is injection normal? It turns out injection is very normal in a lot of systems, and as it happens, we can take a lot of injection examples from biology. Fireflies synchronize their off periods to attract the females so that they don't lose out. So there is a lovely synchronization dance that happens in fireflies. So much so that in females they synchronize their periods, the lionesses, so that the offspring that they have eventually after their mating turns out to have a larger survival chance when you have all the offsprings being born together. In case of fiddler crabs, the crabs are known to wave their arms around to attract the mate. And how does this happen? They look at each other and synchronize the waving. Something that comes very close to our heart is the fact that our own heart muscles always beat in synchronization. If you have thought about it, there is only a lub-dub that happens. This happens because each heart muscle takes information of the adjacent ones and operate in synchronization. Now, all this is okay, but I'm sure we synchronize too. We are part of nature. So I want you all to try an experiment with me right now. What you're going to do is I'm going to be your source of injection. You're going to follow how I clap. Okay? First we are going to synchronize, and then I'm going to slow down, and it's going to be really slow, and then I'm going to speed up. So for the next 2 minutes, let me get your attention. Let's start clapping. Let's just warm up and clap once without me. Good. None of you can synchronize with each other. Thanks for that. Now let's try following me. Okay. Whoa. Very good. You lost it. Okay. Let's go fast now. Good. Faster. Good. You lost sync now. Okay. So in between, there were 2 points where you were in sync with me. Let's remember this. When the frequency is lower, you lost sync, very low. And when the frequency was very high, you lost sync again. But in between, you could follow me fine. So what's happening? Let's understand this as oscillators. If I was clapping independently of you, like in the first time, and we would have a beat frequency, that is once in a while, at the same time period, we would clap together. But if I measured how you were clapping, you in black were clapping with respect to my claps, and I took time traces, like exact same thing, I would see that I would start with the alpha time difference or phase difference in this case, then it would be 2 alpha, 3 alpha, like that, and finally we would sync and then go back to the same phase. So this is beat frequency. Okay. So if there is no injection, there is no interaction. Perfect. This we understand. So there is a beat frequency. However, if I look at it in terms of time overall picture, your clap can come anywhere. And this picture, please keep this in mind. You have a beat frequency effective in this. Okay. Now, what happens if we both had the same clapping frequencies, but you had to follow my frequency? So what you would do is, by influenced by me, you would adjust the delay in your own mind. You would calculate your clapping frequency and you would listen to my clap of the previous trial and then try to adjust your frequency with the addition of those two, and then adjust better next time and better, and eventually you will fall in line with me. That's achieving synchronization. You heard that. Now, this means that initially we didn't have a beat, but initially you started adjusting your phase so as to match mine, and we both clapped at F0, the resonant frequency. So this picture would look like this. There is no beat frequency. These phasers are in phase and they all align. So that is one picture. Now, if there was any other frequency, you'd be tempted to clap at your own frequency, but you want to follow mine. So there is a certain beat frequency that is tempting you to move away from me. So even if you manage to somehow adjust your phase, the temptation will pull you up. Okay? And eventually what will happen is you clap with a certain delay. That's it. And this delay will be maintained. So the beat frequency is trying to pull you away and at a different phase, whereas you're trying to adjust the phase and come back to this point. Eventually you'll end up with a constant phase, and constant phase is fine too. That means we both are still operating at the same frequency. Okay. Now, in the last one, let's talk about the ranges. What happened at the ranges? Just outside of it, you cannot follow anymore. That is the amount of phase adjustment you can do. You're out of it. That's all. So it is at the lower part and a higher part. So you have this picture where the amount of phase adjustment you can do is at its absolute limit. So in summary, what you have is these four states. The locking range, one where you are in synchronization, one where you are edge, and then you are at outside of the locking range. If you put it together in the resonant cavity, you get this. As you change the frequency, either you are at resonance, you are away from resonance with some phase, or you are at the edge. This is seen experimentally also. If I was at different frequencies, as I change my frequency, you wouldn't follow. That's linear. But then where you do follow, this is the range. Our differences in frequency will match. Now, pulses is a different case. If we look at pulses, there are a lot of different modes. Let's look at this picture a little more carefully. What we see is you have harmonics, and harmonics seem to have different ranges that they deviate from this differently. So, how do you understand that? What you have is you start with a slightly detuned frequency, but the harmonic sees multipliers of it. Second harmonic will see twice the detuning, third harmonic will see twice the detuning, so on. So you add the harmonics to it. The minute you add the harmonics, the limits are reached early. So over the n modes, what you have is, if I started with this as the range, which is the difference between the limits, I would hit the range earlier and earlier. So this, you start with the largest range, for the nth harmonic, it just becomes this. So how? This is also seen in experiments. The ranges are hit earlier and earlier. However, how do you explain the pulse width? If you had an infinite bandwidth, all the modes were present, the pulses would be delta harmonics. As you start limiting the modes, the pulses will become larger and larger. So here, you have an inverse relationship to number of modes which are complex. So pulse width is just how many modes are there. So as you detune, fewer modes are there, pulse width is going to increase. With this, what we have understood is, if you give a slight detuning, so higher modes are going to lose injection and the lower modes may still stay. So the pulse width is going to depend on how detuned you are. So further away, when you are away from the detuning range, the pulses won't follow. Whereas within the detuning range also, what you have is the pulse widths are less. With this, we have understood a major aspect of synchronization that is required to get lasers to operate together. I thank you for your patience. I thank my guides for giving me this opportunity, and the bigger picture also is in a lot of cases. So I thank all of the people and my friends and everyone who's there. It's time for a big question.
So, what is the relation of this monkey and deer to the top?
I think nature inspires me more than anything. So, yeah. This has been this is my favorite part of IIT.
Yeah. I asked you because during the talk also there were a few instances of animal behavior. So I was trying to connect whether this also had some.
I'm sure if we search, we will find one. Okay, let's thank the speaker again.